This one's a pretty quick one, so I'm going to run through this one as well. All right, so we've got two spheres, and we're going to treat them as if they're right next to each other. And we release them from rest. One sphere has a mass of 2 grams, the other a mass of 1 gram. Both have a diameter of 2.2 millimeters, so this is 2.2 millimeters over 2. This is 2.2 millimeters over 2. So their distance between their centers is 2.2 millimeters, which is 2.2 times 10 to the minus 3 meters. The charge on this guy is 2.0 nanocoulombs, and the charge on this guy is 1.0 nanocoulomb. And it wants to know what their speeds are when they're very far apart. So we can compute the potential energy when they're next to each other as 1 over 4 pi epsilon naught QA QB over R, which, as they both have the same sign charge, is going to be positive. So we've got 2.0 times 10 to the minus 9 coulombs, 1.0 times 10 to the minus 9 coulombs over 4 pi. Epsilon naught is a constant in coulomb squared per meters joules, and R is 2.2 times 10 to the minus 3 meters. And this comes out to be 8.1705 times 10 to the minus 6 joules. Now, when the particles are very far apart, R goes to infinity, so U goes to 0. So, we're going to have a kinetic energy of KE. So then delta KE is equal to delta U from conservation of energy. So then our delta KE is actually going to be minus delta U, which is, and our initial kinetic energy was 0, so KEF minus KEI is equal to minus UF minus UI. Our UF is 0, and so then our final kinetic energy is just our initial potential energy, which is this 8.1705 times 10 to the minus 6 joules. Our kinetic energy final is 1/2 mVA squared plus 1/2 m, I should have put A's on everything, VB squared, which is equal to this 8.1705 times 10 to the minus 6 joules. So we also have conservation of momentum. And our momentum initially was 0 as nothing was moving. And then our final momentum is MA VA plus MB VB. And so PF equals PI. So then this equals 0. And so then we can solve for VB by saying that VB is minus MA VA over MP. Or for use in our kinetic energy expression, we can say that VB squared is MA squared VA squared over MB squared. Plugging this into our kinetic energy, we have 1/2 MA VA squared plus 1/2 MB VA squared MA squared VA squared over MB squared is equal to this 8.1705 times 10 to the minus 6 joules. So we can cancel one of these MBs and say that 1/2 MA VA squared onto 1 plus MA over MB is equal to 8.1705 times 10 to the minus 6 joules, or VA squared, or VA is the square root of 2 times 8.1705 times 10 to the minus 6 joules, all over our A mass, which is 2 times 10 to the minus 3 kilograms. So converting it from grams into kilograms, onto 1 plus 2 times 10 to the minus 3 kilograms over 1 times 10 to the minus 3 kilograms. And the square root of all that. If we do this on our calculator, we get 0.05219 meters per second. Our VA is obviously going to be to the left, and this is our magnitude of our VA, or just our speed. So I'm going to say that VA is minus 0.05219 meters per second, just to match up with the figure. And then VB is minus, from our momentum expression, our mass of A over our mass of B times the VA we just calculated, so minus 0.05219 meters per second, which comes out to be 0.10437. Okay, so if we check our solution here, so first compute our potential energy when they're next to each other, so 8.18 times 10 to the minus 6, so 8.17, 8.18, just different by rounding. We can use our kinetic energy expression and our conservation of momentum to get that our VB is 10.4 times 10 to the minus 2, so that's that, and 5.2 times 10 to the minus 2, so that's that. So that looks the same, so that looks good, solution is correct. All right, and then I'm actually just going to stop it there and say that's it for today. If you enjoyed this, please subscribe to OneClass. If you want to leave questions, please follow the links below the video. This has been Jeff Krause for OneClass.